Okay. Okay. Yep. Okay. Great. All right. So Sam gave us some very lovely motivation from theory of modular forms, and he mentioned kind of almost in passing this constant term. So he was talking about the case of GL2 or maybe PGL2, right? So we're back to the situation of a general group, then the story is just a little bit more complicated. We have to, talk a little bit about B theory, and so this constant term I wanted to emphasize is kind of an instance of this general phenomenon in representation theory. So if I have a representation of a reductive group of some kind, right? One thing I can do to try to study the representation is to restrict it to a parabolic subgroup, right? And then further take invariant with respect to the unipotent radical of that parabolic subgroup. This is called Jacques functor usually, right? And so I claim constant term is really just an instance of this in kind of the automorphic setting. And this operation has an adjoint, right? In representation theory, we call this parabolic induction. In automorphic forms, the adjoint is called Eisenstein series. So this is what we're going to be talking about is these two adjoint operations. And the idea here, as Sam explained, is to somehow decompose the category of automorphic sheaves into two sort of orthogonal components, right? One of which is generated by Eisenstein series, and the other of which is not seen by Eisenstein series, and that's the so-called custodial part. So that's sort of the point of all of this. Okay, so as usual, you'll be parabolic and just fix this position. I don't really use it. It's M is more canonically pushing P, of course. And then I can draw this basic convolution diagram. So again, how do we do parabolic induction in usual representation theory? We diagram. So usual representation theory, we're starting with a representation, say, of a Levy subgroup, and we restrict along the projection from the parabolic P to M, and then we induce from P to G, right? So the analog of this for automorphic sheaves will be, well, actually, back up just a moment, the functor that's a bit easier to define or that's defined a priori will be the adjoint, the constant term functor. So constant term is going to be, we'll write lower star. There's some other variants of this that we won't talk about at all, but that's the reason for this decoration. Going from D modules on G to D modules on M. Okay, and so it's defined. Well, we pull push along this correspondence first. So make sure I do this in the right order. Sorry, so I start with Quindic, right? So it's Q lower star, P upper shriek. Yeah, goes in the right direction. Okay, this is nice. These functors are lower star, upper shriek. We know that these make sense in the world of D modules, and also there's some shift here which I'll ignore. And the first kind of non-trivial observation here is that this constant term functor admits a left adjoint. And this, of course, would be the functor of Eisenstein series. We call it Eis little shriek. And this is not at all clear, just because, again, if you think about what are the left adjoints of these functors, first of all, Q lower star, actually, the fact that that has a left adjoint is easy because this projection from bun P to bun M is smooth, like in the sense of stacks. The fibers look like bun N, so they're sort of smooth carbon stacks. But what's much less clear is that P lower shriek, right, which is a priori this partially defined left adjoint of P upper shriek, is defined on the essential image of Q upper star. So this is something that must be shown. And the way to do this is to appeal to this construction of Drinfeld's. This Drinfeld compactification. So I think, yeah, if I have time at the end of the talk, I can talk about it. It's a very nice story, but I almost certainly won't. So let me just kind of say this is well, I guess the reference is really the paper from the Gatesbury and Eisenstein series, which is a reference for a lot of the stuff. And then there's also the paper of Trenfeld and Gatesbury on geometric constant terms, so it's another good place to look. So, questions so far?
Oh, yeah, I have one. So the mission of the left hand, this is like a demodulator. This is mainly a demodulator. Like,
It's a demodulation, that's right. If I were to constructible sheets, it would be demodulation. That's right. Okay,
But in analytic sheaves or something, you can imagine this as like a kind of base change assertion.
what's a base change assertion?
Like the existence of a left joint. It
Well,
obviously exists for analytic sheaves, but it doesn't obviously like satisfy good. So they're
Right.
It's like not necessarily a functor defined by a kernel.
There's still something to say in situations where the functor is defined, but yeah, it is upper defined. Does that make sense? Okay. All right. Any other questions? Okay, and another kind of remark here, sort of an aside. We can modify these adjoint functors so that they're really an adjunction on the twisted categories. Right. And this is actually what we want to do. But as others have pointed out, right, we can actually identify. Sorry, to start. We can actually identify the critically twisted categories with the untwisted categories, and since continuity localization will not appear in this talk, I'm just going to completely ignore these twists. I think that's okay. All right. Okay, so the next thing is to define the cuspidal part. So first of all, we'll define its complement, its orthogonal complement. So define D mod bun-G subscript i's. Okay, this is going to be the part that's generated by Eisenstein series. Also category generated by the images of the Eisenstein series functors. I didn't put E in the notation, but if I do write it, it's clear what I mean, right? So as so let's say for all proper parabolic subgroups, right? So this is the part that is generated by Eisenstein series, and then we define the cuspidal part to simply be the right orthogonal complement of this. Or another way of saying it is that it's those objects of D mod bun-G which are killed by the constant term functors for all proper parabolics. Okay. So equivalently, these are objects such that come from any Eisenstein evaluated in any object of D mod 1M, and so such an object is 0. There's no longer a dark side of the board. Okay. Nice. All right, and then the first really non-trivial observation here. So this, I think, is a relatively straightforward generalization of something that already occurs in the theory of automorphic forms, is that these cuspidal objects are compactly supported in a very strong sense. Not only are they sort of individually compactly supported, but they're sort of uniformly so. So what I want to say is that there exists an open substack U such that the following holds. first of all, it's let me say this, U has quasi-compact. So I lied a little bit, not quite compact, it's supported, but sort of in each connected component, right? Bungee may have infinitely many connected components. So U has quasi-compact intersection with each connected component of Bungee. So, for example, G is semi-simple, it's just quasi-compact. And then 2, so for any custable sheaf, it's star extended from this U. There's always this unit morphism, and it's an isomorphism. In fact, something further is true, which is very interesting, which is that it's also Schrief extended. Okay, so in other words, it's very similar to the situation with Whittaker, right, where we have this cleanness assertion. So this is another kind of cleanness assertion. So in fact, these custable sheaves are cleanly extended from some essentially quasi-compact open substack. Okay, and I don't think I have time to comment on the proof, but again, this is in this paper of Trenfeld and Dennis on geometric constant term functors. I think is place to look. Yeah.
So this formula means also the J lower the bottom.
Correct. Yeah, and in fact, for this, you can choose U in such a way that J lower Schrief is defined on all objects of D mod U, so it's one of these so-called truncative substacks. So, but yeah, in particular, it'll be defined on the custable ones.
Is it just usually like extensions of what's the relevant geometry from G?
Probably not. So if you have something to say, I'm encouraged to play.
It starts
Someone else.
looking more like for like
Thingies.
For a parabolic as you go further away from the
yeah.
right. So it's some explicit analysis of the geometry of Bun-P, and it's mapped to Bun-G, and so it's not like super duper deep, but it definitely involves analysis of this this Harder-Nar Simon stratification of Bun-G, which is some combinatorics that I don't want to get into, but
In other words, at some point you need to know something about the geometry of Bungee. We start from geometric language, and we had nothing at all explicit about what Bungee looks like so far.
exactly.
Sort of the point where we run into that where that becomes very fun.
You have to say something, yeah, exactly. So okay, but yeah, it modulo these combinatorics like it's a pretty understandable.
So for GL2 it's variance.
Correct. Yeah, exactly.
Just
Another comment is for P1 there are no custable sheaves, so you can't see it there, which is unfortunate because Dmod but Bungee P1 is kind of very understandable, but yeah.
Quick, one hardware question, is this, there's one U for all F or?
Correct, exactly. That's what I meant by kind of they're uniformly compact with solid. Yeah, exactly.
But also, these things are always forced because we work with big categories. So if you imagine there were different U's, we would take abstracts and objects and force the things to be uniform. So in fact, this kind of.
Yeah, good point. Yeah. So there's no compactness assumption on the X or anything like that.
And you very small in some way, that's small.
Well, yeah, so I'm saying there's a specific view that sort of just only depends on G and X.
Like when you think of those small people, what's the difference between this capital category, what can be cast and what should be?
Well, not everything in Dmod U will be cuspidal. I mean, I think one of these cuspidal things is
I think if you try solving this exercise, even for GL2, you can see the difference. Like the higher the genus, basically, there is a difference between all extensions. Maybe I shouldn't say. So the higher the genus, the harder somehow, the further you have to cut, and the more. The less somehow, well, the more cuspidal and non-cuspidal stuff will mix within this.
Yeah, great. Yeah, I mean, again, it's a uniform construction. Well, like again, it only sort of depends on what G is and of course what X is. So like when you sort of write down some union apart in our Riemann strata, of course, the answer will involve the genus and will also involve row. Have some positive weights. Yeah.
I mean, this sort of this question. So we chose to consist of the semi-stable bundles, or is this more complicated?
More complicated.
The number of strata, the number of hard Riemann strata you need depends on the genus.
Yeah.
But all the semi-stable ones are in.
Yes, yeah, of course. I mean, this is a union of some hard Riemann strata, that's right, that's the thing.
Yes, it's all.
Because that's the biggest open one. Yeah. Okay. Right.
And just to go back to the other one, it's like, it's difficult to describe geometrically what sort of sheaves are possible. I mean, there's this formula for what they are, but it's not like it's just all sheaves on the sheet or something. It's a very, very special sheet.
As in a lot of situations in representation theory, right? The custal objects are the ones that are the most mysterious and hardest to understand.
So you can't compute the more from GL2 cusp. No, GL2.
GL2. I mean,
I mean,
Don't
the
know if I can say
definition
anything more.
involves integration over all extensions of a line bundle by another line bundle.
Mhm.
And the claim is that if degrees of this line bundle differ by a very high number, then these extensions will be, you will essentially get no extent. So you just get a direct sum.
Mhm.
And that's, so U is the complement, like, this is what happens outside of U, that's what makes U exist. But the point at which this happens depends on the genes.
right.
Yeah, it's the Riemann rule.
Other questions? Great. And I think Dennis tells me we won't actually need this plainness assertion, but I mean we do need the existence of this U and let's say custal sheets are star extended.
What about self-duality
What about it?
of Campbell sheets?
I think we're not talking
It will
about
be
this.
discussed tomorrow. That will
Okay.
be separate topic tomorrow.
Great. Okay. Anything else? All right. So great. So now I can move on to sorry?
The M is
M is the Levy quotient of P. So it's the quotient P is a parabolic subgroup, and in it, like for GLN, right? So P is kind of block upper triangular matrices, and M is the block diagonal matrices. And NP is the stuff that's like the blocks along the diagonal identity matrices. Yeah. Yeah, I'm not going to talk about. Well, there's like a CT lore question mark. Yeah, there's various other flavors, and we want. You can imagine you can change where the streaks and stars appear and so on, but these are the ones that I mean. Why am I doing things in this way in particular? I'm about to define a constant term in Eisenstein series on the spectral side, and I want to define things so that they match up, right? That's also the reason why you need the shift and so on. Anything else? So let's move on to the spectral side. Okay, so here I'm going to draw a very similar convolution diagram. And I'll also denote the functors the maps by P spec and Q spec. Okay, so some observations which are going to be important for defining these functors. One is that Q spec is sort of relatively quasi-smooth. Again, the fibers look like Lopsis inchact or twisted forms of that, which is quasi-smooth. And in particular, this implies that it has, I think this was mentioned in Kevin's talk, upper star exists, sort of for info. Okay, so you need some condition for info upper star to exist, and quasi-smooth is sufficient.
You mean to respect?
Did I write B spec? B spec. Sorry. Another observation is that E spec is proper.
Wait, sorry, Justin?
Yeah.
The question, can you just remind us what it means like about the dual parabolic?
What it means to have it, I mean, the standard so like let's say I fix a Borel, right? In B, and then part of constructing the Langlands-Goldberg is you have to fix all of this data, right? Which in particular, it's going to come along with a Borel subgroup inside of the Langlands-Goldberg, right? And then standard parabolics are sort of very rigid, right? You just determine by combinatorial data, which is a subset of the simple roots. And so I just mean the one that corresponds to the same subset of the simple roots, under the identification between simple roots. Yeah.
Thank you.
Yeah. Point. Okay. All right. So another geometric property, P spec is proper. This does not happen on the geometric side, right? The map from bun B to bun B to bun G is sort of famously not proper. But if you think about what the fibers of this map are, for example, the fiber of the trivial check local system is just a copy of the flag variety G mod B. The other fibers look similar, so it's this is actually a proper map, and that implies that P spec lower star is actually left adjoint to P spec upper tree. Okay, so these are important observations, and we define these functors. Right?
So
And
in general, you get some closed subset of that.
sorry.
So like over a general bundle, you get like the flags by that one flag or fixed by one.
Yeah, right. This is horizontal sections and twisted five right here. Yeah. Right? Thanks. Okay. And now, so I want to define spectral Eisenstein series in the constant term as pull push using this correspondence. The way that we've defined the spectral side, right, we have this null potent singular support condition. So in order to kind of define the functors, you have to check something. This is in the original paper of Lehman and Dennis, where they define singular support group sheaves and one. And okay, so the so this is kind of what we want to be our spectral Eisenstein series functor and our spectral constant term functor would be something like this. And the claim is that both of these preserve null potent singular support. Okay. And this is not too terribly hard, but I encourage you to look at the paper. There they prove kind of various sort of punctuality properties for singular support. Okay, and so for the most part, this is kind of a formal consequence of such things. I think the only point at which you have to actually use anything whatsoever kind of about the theory is that if I have an element, okay, so when you talk about singular support, you're talking about, sections of some local systems attached to the cojoint representation or something. And at some point, you're going to use the fact that if I have an element of the dual of G, so if I have an element of the dual of G, such that its image in P lower star, P upper star, sorry, the fractor P is there is the algebra of the parabolic, right? Not the other fractor P, sorry, lands in the dual of the levy and is null potent as such, then alpha is null potent. This is what you need, I think, to show that P spec lower star preserves nilpotent singular support. That's kind of the only place that you actually have to check.
Let me ask you a stupid question. Okay, so like, if I start with the forest and go to G. So I had Q code before, but I did zeros in the support.
I'll comment on this, but it doesn't actually land in Q code. That's what you mean?
That's it.
Yeah, no, that's right. This spectral Eisenstein series, crucially, even if you start with something that has zero singular support, you may pick up non-zero singular support on fine. I'll comment on this. Yeah.
So you the two components preserve open singular support for the individual functors preserve it?
Yeah, absolutely. That's how you check it, yeah. Right. So this other questions? Okay, great. Okay, so now without further ado, I can actually define the spectral Eisenstein series functors. Constant term. Okay, so or I get I's spec will be this first one. And then over here, I'll have the functor in the other direction. And this, of course, is constant term. So. Okay.
Sorry, just representation of it. On the spectral side, we have just one resistance reduction resistance.
Well, there's sort of fewer functors in the theory of quasi-coherency somehow, right? So yeah. Yeah. There's also these like co-things, but yeah, here it's basically it. What questions? Okay, great. So now I'm gonna kind of relate it to Revere's last question. There's theorem also from Dieman Dennis's paper, and this is you can almost think of as the whole raison d'etre for this stuff about nilpotent singular support. Okay, so let me kind of formulate this in two parts. So first of all, I'm going to consider first the locus of irreducible G-check local systems. So this means those local systems that don't admit the reduction to a proper parabolic. Right? Sense? And so this includes into nil. And the first claim is that this is actually an equivalence. And so you should think somehow like if, for example, if the group were adjoint type, then locus irreducible is smooth. Is that right? You see something? Yeah. Is it adjoint type? Is that the correct hypothesis?
Well, just G is that.
Just semi-simple is okay? Yeah. So it's semi-simple, then locus, yeah, sorry, it's a right. So if G is semi-simple, then this is actually smooth, and so this is sort of clear because it's actually an equivalence to just all of INSCO, right? And for a reductive group, kind of need the nilpotent part because you think about this. It isn't quite true for like a torus, for example, where you have this derived part, but the nilpotent singular support sort of takes care of that. And then point two is that basically if you take sort of this part, quasi-co, or even just the part of quasi-co that's star extended from the irreducible locus, and you take all of the spectral Eisenstein series functors, their images, then this is going to generate everything. When we say by QCO, and the essential images of all the spectral Eisenstein series functors for proper parabolics. And specifically, I guess, you just say, yeah, it's the essential image is even of QCO.
You shouldn't have treat because we decided.
Oh yeah, sorry, I meant the spectral. Yeah, of course. Thank you. Sort of for all problem terms. Okay. And so this tells you not only do these functors preserve nilpotent singular support, but in some sense, you kind of started out life interested in quasi-co and you wanted to enlarge the category as mildly as possible, as little as possible, right? While still having these Eisenstein functors available, then this is sort of the minimal category that you can get away with. Make sense? I could say, so like, yeah, if I want it to be kind of as economical as possible, I could say things star extended from LS irreducible, but that in particular is contained in quasi-co. So, other questions?
So is this analogous to a statement on the D module side?
I mean, yeah, it's kind of analogous to, well, over there it was sort of a definition, right? Because it's ultimately the custodial part is going to correspond to this, right? So it's sort of tautologically, the way we define the custodial part is generates D mod bun G along with the Eisenstein part. So
There was like taking the combo things that talked about. Okay.
yeah. So,
And there's
So like,
You get all of the mod from bungee by applying highest extent of the modules for heavy and.
right, exactly. In accordance with kind of the general philosophy of parabolic induction.
we can do it the other way and change this statement and say that if you take input needle, you can do another aspect of quasi-core for parabolics, you will get exactly quasi-core for the reduced.
Other questions?
So just, you said that here you can put irreducible in the Q code on the second time.
Yeah, as long as you understand that. Yeah, exactly. Understood as a subcategory via like star extension. Yeah, J-Lord star, such things. Yeah.
And the reason it's written like this is because here all the embeddings send compact to compact. So I'm extending from an open to from a reduced from does not preserve.
Right, yeah.
So it's nicer to write it the way it just
To get kind of compact generators, but and also again, because my sort of my philosophical explanation of this was again that like this justifies why input and help is sort of the minimal enlargement of quasi-code that sort of allows for Eisenstein series functors.
But I just want to stupid origin for people to
Sure.
The singular support estimates, they're all happening inside shifted for tangent fibers, but they're just like completely familiar thing from the finite dimensional case of like
Yes.
the Springer theory played with the moment maps for partial flag varieties.
Yeah, I mean the spectral side in general kind of has this way. So it's
The bigger it's just kind of finite dimensional geometry going on, just a tangent fiber everything.
exactly. Once you get over your discomfort with derived algebraic geometry, and sometimes the spectral side is much easier for many things of this nature, right? Maybe this is okay. Anyway, so maybe it's controversial to say. Just in things of this nature. Okay. Other questions? No?
Yeah, we're good.
Okay. Okay, so now I have to give a trigger warning. I'm going to say the words unital local to global functor again, so sorry if you were. I know that for a lot of people probably this is part of the program is kind of a nightmare, but the thing about nightmares is that they're often recurring, so okay, so what are we going to do with these Eisenstein series and constant term functors? Again, the whole idea was to somehow prove Langlands now that we have a functor in one direction, right? By sort of proving it on decomposing the category of automorphic sheaves into sort of the Eisenstein part and the custodial part, and then proving it separately for each of those two components. So I think Dennis will comment later on the proof for the Eisenstein part, and tomorrow will be about the custodial part. But how do you actually prove that it's equivalence on the Eisenstein parts? Well, first of all, you surely need to show that the Eisenstein and constant term functors actually correspond under the Langlands functors that we've already, or intertwined by the Langlands functors that we've already defined. And how do you do that? Well, by a local to global argument, like everything else that we've done. So sorry, it's sort of doing chiral. So what I'll do is I should say it's sort of spectral constant term. So I'll explain how to write a formula for spectral constant term in some local terms, essentially, which will allow us to more easily compare it to the automorphic side. This will be explained later like this. Okay, so first of all, I need to kind of say what is the local analog of constant term? Okay, so I'll just be very naive and say, well, I have my local avatars of the spaces of local systems and take this kind of version over the non-punctured disk. Remember, at a point, these are just classifying stacks. And I'll just, yeah, so I guess I'll call these p-spec loc and q-spec loc. Okay, and let's see, over here. So these guys are smooth. So there's nothing about quasi-code versus inspo here. So the local analog of constant term is, again, it's a kind of Jacquet functor, as I mentioned earlier. So that's hence the letter J. And it's going to be pull push again. And here, because we're working with quasi-coherent sheaves, there's only upper star. And this is going from quasi-co looks this G check reg. Okay, so this is all well and good. It looks very analogous to the global situation. On the other hand, for, as Gerbier would say, human beings, there's a just much more concrete description of this functor. So another way to say it is we know that, again, these are essentially classifying stacks. At a point, they literally are, and factorizably, they're this factorizable version. So this is really just ref g check and ref in check. And in fact, this is like the kind of obvious Jacquet functor you would expect. So the way to say it is it's first you restrict the G check to P check. And then you take invariance with respect to the input and radical. Which is then acted upon by in check. So in other words, this is the right adjoint of the restriction functor along the projection from P check to M check. So you can see very easily why it matches up with these functors in that way. Okay. And lastly, let me comment that this is what we call a lax unital factorization functor. Why? Because restriction of representations is, for sort of very tautological reasons, just strictly factorization, strictly factorizable. And this is right adjoint to a restriction functor, and therefore inherits this kind of lax factorization structure. In fact, it strictly factorizes, but it's only lax unital. So you can see this, I mean, more concretely, all I'm saying is that if I take the trivial representation, right, which is the unit here, and I take in check invariance, NP check invariance, like famously that's not just scalars, it's this Chevalier-Eilenberg complex. So that's it. Questions about this? So this is going to be our local avatar for the constant term functor. And I'll start writing down the global functors. Like I promised. So when do I need to stop? Anybody? Just keeping track. I think I started at
12:40.
12:45. Okay, somewhere in all right, so let's write this look at the global expression for constant terms. I promise, I mean spectral constant term. So I'll draw a square. All of this is going to look quite familiar if you were paying attention yesterday. Very analogous to some things that appeared in Lynn's talks. Okay, so now I'm going to follow this funny notational convention, which you can probably safely ignore, where we use the plain character rep g check or whatever for the factorization category. And if I want to ignore the factorization structure and just think of it as the sheaf of categories on mutable Ron, I put it on the. And I want to do this because I'm going to be writing things downstairs, which are just these kind of constant sheaves on mutable Ron that are very much not factorizable. Okay, so now here we'll have our spectral constant term functor that's sort of constant along mutable Ron space. Okay, and here is our low spec, which has been discussed quite a lot. This is for G check, and likewise over here for M check. And here we have, as I said, the spectral constant term, sort of constant along the mutable Ron space. And so this is a diagram in sheaves of categories on mutable Ron space. And let me write the plane. So you might wonder, well, if you weren't paying attention yesterday, you would probably say, oh, probably it's going to say that this commutes. And that's great, because then I can sort of take global sections on mutable Ron and I would get this promised local expression for spectral constant term, but life is not so easy, and we have to use this this integration along insertion of the unit procedure that they introduced. So the point is there exists a natural transformation of lax unital local to global functors they split up here to be closer to right. So it's going to go from this upper right leg to the lower left leg. And let me call this, I don't know, call it eta or something. So means there exists such an eta. And it's not an isomorphism, and we can kind of see this already from if you stare at this, you can convince yourself that the lower left leg is actually a strict unital local to global functor. We sort of know this already for the low spec, and on the bottom you're just doing something that's constant along Ron space. But the upper leg is not, basically because this functor is lax unital, it's not. Fair to say. Okay. So it sort of can't be an isomorphism, but wonderfully, if we just universally force the upper right leg to be a strictly unital local to global functor in the way explained by Nick, then it will become an instance.
Seems that you are saying something like there are more extensions of local systems than just than you see over a formal list. Like the one functor is defined when you go between rep E check and rep M check.
Right.
The fiber is different from the fiber that you see from local systems of a D check to local systems of a A.
And I think we have time for me to explain the proof, so we'll analyze this, right? Yeah, thank you. Good. So okay, and then this induces, therefore, again, this procedure of integrating along insertion of the unit, remember it was the left adjoint of the inclusion from the lax unital local to global functors into, from unital local to global functors into lax unital local to global functors. So therefore, by adjunction, we get a natural transformation from eta like so. And over here, we'll have the other circuit. And the claim is that this induces on itself. And it was almost probably the hard to parse, so let's just stare at it for a second, make sure everything else. Yeah. So this is this.
It's a big thing.
Sorry?
That's the thing they call foods.
Did they call it? I thought he called it. I thought he used the symbol.
I call it
So some
linear effects.
yeah, that.
Okay, yeah. So this is again this procedure that takes a lax unital local to global functor and universally in a left adjointy way forces it to be strictly. Yeah, and so we get this by adjunction from eta. Okay, so this is I won't write the symbol. This thing applied to the natural transformation eta. Yeah, he claims that this is an isomorphism, and again, it's a very abstract statement. I understand that. We have about 15 minutes left, so I'll try to sketch the proof, and we'll kind of understand what's going on, hopefully in the process. Any questions before I do that?
I just have a stupid song, but if we were in the batting setting, like if you should literally take rep check on, nothing to rep check on, like oh, this is very
Did you say that this square doesn't continue as a uniformity, but you say that the underlying thing on the run is.
No, I mean just as like any functors, it doesn't commute. I evaluate an object in the upper left and do the two circuits along. Yeah. I mean somehow the property of being an isomorphism is okay. Anyway, yeah. So. And we'll see this failure to commute explicitly. More or less. Okay. So first sketch. Okay, so first of all, this low spec, we've sort of seen two variants of this, and I think this was addressed in Kevin's talk, but the way that you get low spec to take values in inspo nil is you just simply do the version that lands in quasico, and then you put quasico inside of inspo. So it's nothing fancy. So this is going to mean that I can replace the lower leg by just the kind of analogous functor for quasico. So I'll just call this thing low spec as well. I mean, I think it'll cause some confusion, but and then here we have the version for inspo nil that I wrote over here. And here we have the inclusion, inclusion of quasico into inspo. Okay, and this is by definition this. So this means I can simply replace the bottom leg by the categories by quasi-co when I make the following observation, which is that there's a sort of quasi-co version of constant term, and it's compatible with the int-co version in the following sense. So this is explained in the ranking gates for it. It's again, it's something kind of just very concrete about the geometry of these stacks. So this is what I'm going to call constant term stack quasi-co. We'll find in just a second. And this square commutes where constant term spec quasi-co is just, well, it's kind of the only thing you could write. So it's u spec lower star, e spec upper star in the quasi-co sense. Okay. Now, this is not true in just like total generality for like a random correspondence, but again, it's going to use basically two facts. One is that all the stacks in sight are quasi-smooth, and the other one is that the projection from locus p check to locus sim check is relatively quasi-smooth, and sort of using these, you'll be able to prove this diagram commutes. Some compatibility between int-co pull and push and quasi-co pull and push under these types of inclusions. Yeah, right. I mean, again, it's sort of, depending on which functor you're talking about, it's either the kind of absolute quasi-smoothness or relative quasi-smoothness that matters. Yeah. Okay.
You're saying like when you apply Eisenstein series, these theories and those support for when you apply constant term don't increase.
Yes. Yes. Great. Yeah. Other questions?
I can ask you the opportunity is something analogous to in the natural study, you have to normalize your function, so functions are become modulus function of the parapoint.
No, that's kind of here, but we're suppressing it. Yeah, there are these row twists and stuff. That's what you mean. Like, is that? Yeah, but it's kind of separate. It's kind of a separate issue. It's something that's also here, but I'm kind of, I mean, yeah. Like I mentioned at the beginning that you can twist things so that everything goes between the critically twisted categories, and so you need those twists around if you want to be in the critically twisted level, but I'm just suppressing that. But it all can be decorated with this. Other questions? Okay. Just say a few words about the proof now. I guess I can do here. Okay, so as the upshot of these two boards, right, I can replace the bottom leg of this square by the same, but with quasi-co and constant term stack quasi-co. Agreed? Okay. So now what I'm going to do is I'm going to decompose that square into two squares. So I'm going to go, remember when I do constant term, first I go from G to P, and then I go from P to M. So I'll analyze each of those operations separately. So the first one is the easy part, because this is just restriction. Really? Okay. And so, of course, the vertical arrows are loc spec. This one is yeah, thank you. And this is restriction, star restriction along P, constant along round space. And I claim this more or less tautologically just strictly commutes. Okay. Again, both of these functors are sort of given by restriction. And as remember, this log functor is up to tractability of the round space stuff is basically also given by restriction, right, along this evaluation map. So this is essentially tautological. Okay. And so now it remains to show that the sort of other square, decompose that square into this square, there's going to be a second square involving P and M. Let's follow. Okay, so save my wrist. So draw the same diagram, same square. Replacing the inclusion of P check into G check by the projection from P check onto in check. Okay, and then pass for right adjoints of the horizontal functors. Okay, and so what we'll get is the square, I guess I'll right over here.
Can I ask?
Sure.
I forgot. By definition, left spectrum and other spectrum, so quasi-core, no.
That's what this says.
It's something else.
Yeah. It's that word. And 5 more minutes. Right, so if I draw the square, so here I'll have invariance. And the vertical functors are localization as always, and this one is push forward along Q spec. And a priori, we just have a natural transformation in this direction coming from the fact that, again, it commuted on the nose before I pass the right adjoints. When I pass the right adjoints, it commutes up to a natural transformation. And so now the claim is that when I apply integration along insertion of the unit to the upper right leg, okay, that it becomes an isomorphism.
Is this a general set? If you take this joint, it's not
No, I have to solve personally. Yeah. Because I operate this in the attributes and I solve personally to show strictly units. So it needs something very specific. See?
But back to here, using the fact that Lynn said, right, that you like break it up into two things and one of them already okay, to fix the combination.
Ruby, we should talk loud, we don't finish it.
Are you just saying that like this integration against insertion of the unit is compatible with composition of functors?
Yeah.
Yeah. Okay. It's very believable, so I just didn't say it.
Yeah.
Okay, so we want to show that this is an isomorphism. Yeah. Okay, and then we'll be done. As Ruby says. Okay, and so how do we do this? Well, in fact, it's enough to do it. I can just, and maybe this is not strictly necessary, but it just kind of makes the exposition simpler. So it's enough to show after doing base change along some arbitrary field value point of local system in check. Okay, in K here, I do a lot of arbitrary field extension, but we've seen this kind of thing before. And just let me just say for simplicity, let's just take it to be the trivial local system. The general case is very similar with some twists. Yeah. Okay. And so then what we find is we have to show the following square commutes. So again, I'll take that square and I'll sort of break it into two parts. One is a square involving restriction from p check to n p check. And that part again is no problem whatsoever for the same reason as the that square over there. And then so the last thing to show is that there's one further square. So okay, and this is Luke, this is global sections, right? It was the Q lower star before, so now it becomes global sections, now that I base change to a point. Sorry, now I'm probably out of time. And now this becomes a very concrete statement, and in fact, it's in some sense, like with a small caveat, it's essentially a special case of one of these calculations that Nick did in his talk. Okay?
This.
Nick stated it, I think, right? Carl? Factorization homology was communicated.
For a fine event, Lynn.
Oh, Lynn talked about the
Lynn talked about.
as good as outline. Oh, he did. Okay, great. So
it actually, yeah.
beautiful. Yeah, so let me just write the formula. So here's the concrete thing that you're actually doing here. Taking variance. So first of all, this is a unipotent group, therefore it's generated by the trivial representation. It's enough to show that the square commutes after evaluating the trivial representation. So this is just this kind of Chevrolet-Eilenberg complex, and the natural transformation looks like so. And this is an isomorphism by this calculation of Carl homology for commutative factorization algebras. It's not quite an affine thing, it's not connective, but as we've seen, this is actually okay. That's it.